Hi there, folks. Today we're looking at the Pythagorean theorem and its converse. And, the Pythagorean theorem was one of those things that you've probably seen and done quite a few times in a couple different contexts throughout the years. But we're going to expand upon the Pythagorean theorem just a little bit here. All right, so the Pythagorean theorem we should know as a squared plus b squared equals c squared. And it's referring to the side lengths of these of a right triangle. The big important thing here is just have to make sure that the thing that's by itself is the longest side is the hypotenuse. So C always has to be the hypotenuse. So if a triangle is a right triangle, then the sum of the squares of its legs equals the square of the hypotenuse. Again, it's that a squared plus b squared equals c squared. And the thing that has to be by itself is the hypotenuse, is that longest side, okay? When we talk about the Pythagorean theorem, we talk about Pythagorean triples. These are basically just sets of three numbers that essentially work for the Pythagorean theorem. And when we call something a Pythagorean triple, typically we're talking about whole numbers that basically satisfy the equation, all right? So if we're talking about a Pythagorean triple, we're just talking about a set of whole numbers that you can plug into the Pythagorean theorem and it works, okay? And so that idea that we have these special sets of numbers that come in these sets of three that work for this thing. We just call them Pythagorean triples, okay? For example, if we look at something like this guy, I'm just going to do my Pythagorean theorem to find the missing side. And again, when you look at this thing, the missing side on this one, this is the hypotenuse, which I'll call it C, just because that's what we call it in the context of our Pythagorean theorem equation. And so when we look at something like this guy, I just plug away. I say, okay, 2 squared plus 3 squared equals c squared. All right? And it's not really important in terms of which one of these is a and which one is b. I could just as easily have written this as 3 squared plus 2 squared, okay? The legs are interchangeable here in terms of a and b. The only thing that has to be locked into place is that c has to be the hypotenuse, okay? And so when I look at this, that gives me a 9 plus 4 equals c squared. That's a 13 equals c squared, and now I take the square root of each side. All right. If this was algebra, we'd say, the c equals plus or minus the square root of 13. But in geometry, we only care about that positive value because we're talking about the length of the side of a triangle. So that's the exact value. I could also plug this into a calculator, and really, it depends on the context, all right? The reason that we do the exact value sometimes is because we want to use that to find other values, and we don't want to use a rounded off answer to get more answers, okay? And so that's why it's important to be able to do both of these. For the context of this particular problem, makes more sense as probably a decimal, so 3.6. Okay? But again, the question will ask for different things. Sometimes leave it in radical form or give an exact answer. That just means simplify the radical but leave it in terms of square roots. Okay? If it says to round it off, well, then you plug it into a calculator. All right? If you look at this one right here, when you look at this, again, you could call this missing side A or B. It doesn't matter. Most students are comfortable calling it B because they like A to be the shortest side and B. But again, A and B don't matter in terms of which one is which. So from here, let's see, that's 6 squared plus b squared equals 10 squared. And now I solve this thing. I'm going to have to subtract that 36 from each side. So I get b squared equals 64. And then I take the square root of each side. And this time, the exact version and the plug it into the calculator version are the same thing because this one's a perfect square. So I just get b equals 64, okay? Or sorry, 88. B equals 8. Oh my goodness. Okay, so b equals 8. I almost forgot to take the square root there. But again, that's the exact version and the rounded off version because we didn't have to round this one off, okay? And the other thing here is you could have a equals 8, and that would be acceptable as well. Because again, a and b are interchangeable. It doesn't matter which one you ended up using for your particular equation. I used b, so I ended up with b equals 8, all right? For these guys, it says, which of the following is not a Pythagorean triple? And when we look right away, we see one that we should recognize from the previous example right here. 6, 8, 10 was the triangle we just did. There's a 6, 8, 10. So we know that's a Pythagorean triple because we just used it within the context of our Pythagorean theorem. So this one was a Pythagorean triple. And, maybe I just go right down the line. You might recognize another one of these. A lot of times students recognize the 3, 4, 5. That's one that comes up a lot. But 3 squared plus 4 squared equals 5 squared. And when you look at this one, it's a Pythagorean triple because when I work this out, these are indeed equal to one another. 25 equals 25. That makes it a Pythagorean triple because it works for the Pythagorean theorem. And in terms of where you plug in each of these things, the biggest side has to be the hypotenuse. So when we're plugging this in, the largest side, the 5, had to be the thing by itself, all right? In a right triangle, if this thing is going to be a right triangle, then the largest side has to be the hypotenuse, all right? This one, the rest of these you probably don't recognize, so we just plug them in. And let's see, that gives me a 25 plus 144. We want to see if that equals 169. And when I add these up, it does indeed give me a 169. So yeah, this one is also a Pythagorean triple. Let's check the last one just to make sure Mr. Jansen didn't make a mistake here. That would be hilarious if they're all Pythagorean triples. That would be a pretty sneaky thing to do. And so again here, that's 64 plus the 169. Equals, that's going to be a 225. And, if you need to use a calculator for some of these, if you don't have all of your perfect squares memorized, that's okay. All right, grab a calculator. And then continue with this one. If I add these guys together, that's a 233. And that does not equal to 225, so this one doesn't work. Those are not equal, which means this one is not a Pythagorean triple. Okay? So the converse of the Pythagorean theorem is really the same thing but in reverse. The original, the Pythagorean theorem itself, basically says, hey, if I have a right triangle, then a squared plus b squared equals c squared. All right? If I have a right triangle, this thing works. Well, now it's just the reverse. It's saying, hey, if a squared plus b squared equals c squared, if this thing works, then I must have a right triangle. All right, so it's just saying the same thing backwards. Originally, we had a right triangle, and we knew that the Pythagorean theorem, that formula would work. Now we're looking at it from the perspective of if the formula works, now I know it's a right triangle, okay? And so when you look at this, it says, could each be the sides of a right triangle? And so essentially, we're kind of doing the same thing where we're checking to see if this is a Pythagorean triple. And if it's a Pythagorean triple, then that means those sides could represent a right triangle. And so for this one, you just have to be careful. I don't have this written in the order that maybe you would expect. And so for this one, I'm just going to go smallest to largest because that's the easiest to make sure this thing stays organized. But really the key is this. The 26 has to be the thing that's by itself over here. Okay? And the reason for that is because if this thing is a right triangle, which we don't know if it is yet, then the hypotenuse has to be the longest side. Okay? And so I have to test it with the longest side in the position of the hypotenuse, okay? And so once again, we simplify this thing. The 10 squared is 100. 24 squared ends up being a 576. And the 26 squared ends up being a 676. And now when I continue to simplify, here's that 676 equals 676. And so basically the formula worked. A squared plus b squared does indeed equal c squared, which means this one could be the the side lengths of a right triangle. So we're just going to say, yes, this could form a right triangle. Okay? And again, we're just working backwards, saying, hey, if the a squared plus b squared plus c, a squared plus b squared equals c squared works, then I could use this for a right triangle. If I look at the next one, same kind of thing. And once again, you just have to make sure you put these in the right place. The one that's important is the biggest one, the 10. That has to be the hypotenuse, okay? So it's 4 squared plus 8 squared equals 10 squared, okay? And that gives me a 16 plus 64 equals 100. And right away, you can already tell that this thing is not going to work, all right? So as soon as we see it's not going to work, you could stop and say, all right, not a Pythagorean triple, which means this is not going to be a right triangle. So no, this one can't be a right triangle. So no right triangle for this one, okay? There's no way that I could make that work. And then again, this, this one, make sure you list them in the appropriate order. This would be 10 And you could put the 15 first if it makes you more comfortable. Just always go least to greatest, and you're less likely to make a mistake that way. Not that it matters. The 15 and the 8 can be interchanged here. Okay, the one that's important is that 16. The 16 has to stand alone. And right away, before I even add these things together, I can tell that it's not going to work. All right. So really, you could stop right there and say, no, these aren't going to work. That is not a Pythagorean triple. But here it is. So no, not a right triangle for this one. Okay. And what's interesting, when you look at like the 289 here, if you know your perfect squares, 289 is 17 squared. All right. So really, I could make this a right triangle by, instead of having a 16, that if I had a 17 instead. Okay. All right, so if we look at these guys, these are probably the pieces of this thing that are maybe new to you. Most of us already knew the Pythagorean theorem. Most of us knew the converse of the Pythagorean theorem. We knew that that theorem works both ways. But now we're going to expand this out. And again, this relates back to our knowledge of triangles and the idea that there is a relationship between the size of the side and the size of its opposite angle, or the size of the angle and the size of its opposite side. And so if you think about it, if I have a right triangle and the Pythagorean theorem works, okay, we're kind of testing to see if the side lengths squared are equal to that hypotenuse squared. And there's a relationship between this 90-degree angle and this hypotenuse. And so if you think about it for a second, if I were to change this hypotenuse and make it a little bit longer, okay, what would happen to the angle that's across from that? Well, the angle would have to get bigger to accommodate a longer side, okay? And if I were to make this side shorter, if I were to kind of take this and make the hypotenuse shorter, what would happen to the size of the angle across from it? What would happen to that 90-degree angle? Well, it would have to get smaller. And so the idea here is, when we do the Pythagorean theorem, we can not only just test to see if I have a right triangle is if they're equal, but if that hypotenuse ends up giving us a bigger value than the sum of the other sides, well, then that means the hypotenuse is essentially too long. And if the hypotenuse is longer, then that 90-degree angle must be bigger than 90 degrees, okay? Which means I would have an obtuse triangle. Likewise, if the side that's by itself, if the thing that I'm testing as the hypotenuse, it comes up short, if it's smaller than the sum of the legs squared, well, then that means that side's not quite long enough. It's too small to be a 90-degree angle, which means it must be smaller than the 90 degrees, the angle across from that, which means it's an acute triangle, all right? And so the Pythagorean theorem testing this thing doesn't just give us whether the thing is a right triangle or not, all right, but it also can tell us what kind of triangle we're dealing with, whether it's obtuse or acute, okay? And that's all these are saying. If the square of the longest side of a triangle is greater than the sum of the squares of the other two sides, in other words, I tried the Pythagorean theorem, but the thing that I was figuring for the hypotenuse was too big, well, then it's obtuse triangle, because the angle across from that side that's too big must be bigger than 90 degrees, okay? If the square of the longest side of a triangle is less than the sum of the squares of the other two sides, so again, if that third side, that hypotenuse side, or the thing that I was figuring for the hypotenuse is too small, well, then the angle across from it must be smaller than I was figuring, so it must be smaller than the 90 degrees, so then we have an acute triangle, okay? And so when we look at something like this guy, we just look at it this way and say, okay, classify each as right, obtuse, or acute. And so we're kind of approaching this the same way we did before. We're plugging it into the Pythagorean theorem. And if I plug this into the Pythagorean theorem, once again, I'll go least to greatest. I just have to make sure that the longest side is by itself, okay? The longest side, the one I'm kind of figuring, I just did a degree symbol there instead of a square, but that's the one that I'm kind of pegging as the hypotenuse if it's a hypotenuse, okay? So I have to have the longest side in that spot. And now from here, I can go ahead and plug away. So let's see, this was a 100 plus a 576. And this was a 676. And we already did this example earlier, and we found that, yes, this thing was a right triangle. But essentially, the question isn't a yes or no question now. We're not asking, is it a right triangle? We're simply asking what kind of triangle is it. And so for this one, I would say that this is a right triangle. Okay? It's not a yes or no question. Now I'm classifying the triangle as a right triangle because those two values were equal. All right? If I look at the next one, same kind of thing. We already did this example once, but now we're going to do it in this context. Again, make sure the 10 is the one that's by itself. All right? If the 10 is the one that's by itself because it's the longest side, all right, that's the one I'm pegging as the hypotenuse if this were to be a right triangle, which we already know it's not. Anywho, this one 16 plus the 64 equals the 100. And so that gave me 80 equals the 100. And so when you look at this from the context of, okay, it wasn't quite a right triangle because those were not equal, the side that was by itself, the thing that I was figuring as the hypotenuse over here, is too big. Notice this side is bigger than this side. The hypotenuse is too big. I would need a smaller hypotenuse in order to get a right triangle. And so once again, if the hypotenuse of the triangle is too big, it's too big to be a right triangle. It means the angle across from that must be bigger than 90 degrees. So this one's obtuse. Okay? And again, I always just think of it this way. I look at it like this. Like if this is a 90-degree angle, then we have equivalency here. All right? But if this guy is too big, like if I make that hypotenuse side too big, if I make it bigger than it's supposed to be, now all of a sudden this guy is bigger than 90 degrees. Okay? And likewise, if I make that side too small, well, now this side is less than 90 degrees, okay? And that's kind of what I'm testing here. So as I look at these, I just look at the thing that I had as the hypotenuse and ask myself, is the hypotenuse too big or too small? And if the hypotenuse is too big, then the 90-degree angle, instead of being 90 degrees, is actually bigger than 90 degrees. And if the hypotenuse is too small, well, then that angle must be smaller than 90 degrees. It's that relationship between the opposite side and the opposite angle, okay? And so if I look at this last one here, once again, I'll just put it in order from least to greatest. And again, the one that's important is that 16 has to be by itself. And so as I simplify this, this was 64 plus 225 equals the 256. And that was a 289 equals the 256. And so once again, the key is the side that was by itself. It's that hypotenuse, or the thing that I expected to be the hypotenuse. And when I look at that, the hypotenuse side was this guy. Well, that's too small, which means the hypotenuse is smaller than it needs to be in order for that to be a right triangle. So that's not a hypotenuse. It's not a right triangle. That was too small, which means that the angle across from it must be too small. So instead of being a 90 degree, it must be smaller than that, which means this is an acute triangle. Okay? So again, it's just a Pythagorean theorem, which we should already be familiar with. The a squared plus b squared equals c squared. That only works for right triangles. And if I have a right triangle, it will always work. Okay? But then expanding that a little bit further, all right, if I look at the Pythagorean theorem and the hypotenuse side comes up short, well, now it's an acute triangle. If the hypotenuse side ends up being too big, well, now it's an obtuse triangle. So we can classify these things further using the information that we get from the Pythagorean theorem. Okay?